Okay, so we have a lot of stuff to cover today, and I hope that I can finish everything. So let's start it. Uh, so next we are going to talk about collective communication, and from the previous example, you can see that in the code of a previous example, uh, there are, when we want to send data uh, from every process to process zero, then we have to use MPI send and MPI receive, and but uh, that could be inefficient. MPI MPI provide a number of programming interface that allow you um, uh, to collect information from every process more efficiently. So, for example, if you want to calculate if you want to accumulate data from every process into process zero, uh, you can do like this. Suppose that every process from process zero to process seven, that is, 8 process, and suppose each process have data like process zero have 5, process one had 2, and process 2 has -1, and so on. And you want to collect this information, you want to sum them up and let uh, at, and get a result at process zero. So one way to do it is to use this kind of tree structure communication instead of using for loop to receive data from every process and let every process send data to process zero. You can just it's better to use this kind of communication. This is binary tree like communication. So process 0 and 1, process 1 send data to process 0, and 3 send at the same time 3 send data to process 2. So in this example, 1 send 2 to 0, and 0 already have 5. So 5 plus 2, you get 7 here. And at the same time, process 3 send its data to process 2, and 5 send its data to process 4, and 7 to 6. And upon receiving that data, the receiver process add its data to the one that uh, the one being sent from the other process. So process 2 would have -4, 4 would have 11, and 6 would have -5. On the next step of communication, 2 would send data to 0, and 6 would send data to 4, and finally 4 would send the result, its local result, to 0, and process 0 would calculate the final output. So in this kind of tree-like communications, uh, suppose that I have n process, okay, and n is the power of 2. So uh, how many step, how many communication step, uh, how many communication step do I need to get the result? This one I have 8 process, right? And uh, the number of step is 3. The first step is this level, The second step is this. Uh, the first step is this level. The second step is this level, and the last one is here. So if I have n process, and n is the multiplication or the of 2, then how many steps does it take to get the final result at process 0? Let's say if I have 16 process, how many steps? 4 stages, right? So if I have n process, then that it would be log n, log n. And you can have a different kind of tree like communication pattern. It doesn't have to be the this one. It could be different like this. But the number of steps to perform to calculate a global sum is uh, much better than the is much better than in the trapezoidal rules example. So MPI provide this kind of mechanism for you, and but you don't have to. But you don't have to write this communication pattern by yourself. You can use MPI interface for that, and MPI has an interface called MPI reduce. Uh, so MPI reduce in MPI reduce you have to there are a number of parameters here. The first one is the input parameter. So you have to give the memory address of the data that you want to send, that you want the MPI reduce to accumulate the data for the first parameter. The second parameter is the output, and this will be the MPI would calculate the final output for you, and that final output will be assigned to this variable. The next one is the count. Um, you can instead of calculate just one number, you can calculate a vector of uh, an array of number, and every element in the array uh, would be uh, would be calculated, would be operate on simultaneously. And the next one is the data type. So for input and output that you want to accumulate data, um, it could be of particular type, and you have to specify the type here. Next one is the parameter. Um, when you want to do a global operation, it could be the global sum, the global maximum. If you want to find a maximum value or minimum value, it could be a global maximum or global minimum, uh, or it could be a global multiplication and so on. And the the next one is the destination process. So for MPI reduce, you would specify the rank ID of the process that uh, you want MPI to um, give the result to that process, and it will be more clear in the example. So this is we call this process a root process. So for example, in the previous example, in this tree structure, the root process would be 0, would be rank 0. The last one is the communicator. And there are a couple of example here. In the first example, this come from the trapezoidal rule. Uh, so instead of using send and receive, you can use MPI reduce, and you can send the local in or local integral to process 0. And to do that, you specify local integral here, and the final output, that is total integral variable here, a number of one. This one means uh, the number of variable is one variable, and the information being passed among MPI process is the double, is of type double, and the operation, the global operation is summation. So and after MPI uh, add every local integral being passed to it from every process and get the result, then uh, it would assign the result, the final result, to the total int variable on process 0. So this is where the final result would be assigned to uh, on at this particular process. This process 0 could be changed to something else, and that other, I mean, after you change this to something else, that process would be the one that the total in uh, would be assigned the final result to. In this example, MPI allow you to do the global sum uh, for 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 an array of an array of data. So in this example, suppose you have an array of n. Every process has local x, an array of size n of local x, and you want to add every element of local x of every process, and get and put the result in sum x here, sum of n in this array, sum of n here. Then you would do it like this, um, and you have to specify the number of element to n and the type of every element as double. So the type of operation that MPI reduce support are max, min, sum, product, and logical and bitwise, and you can also define your own operation, and that you have to look at the MPI, more MPI material from the internet. So let's take a look at and this example. Suppose that every process have a y value of 0 and the x value of uh, specified here, and we want to use MPI reduce to reduce to reduce to summarize the y value of every process to process 0. So and suppose that uh, the communication pattern for MPI reduce is a tree-like data structure. It's a tree-like communication pattern like this. So in here, at process 0, process you have process 0 here, and 1 and 2. And in this picture, process 1 would send data to process 0, and so what being calculated at this stage of communication after process 0 receive data from process 1, process 2, uh, it would be x would be 10, 10 plus 40. So this would be n plus 40, that is 50. And for this, and at the same time, process 3 send data to process 1, and Since x on process 1 is 20, x1 on process 3 is 2, so 20 plus 2 would be 22, and finally 50 plus 22 on process 0, that would be 72. Um, so process 0 would assign 72 to y variable here. But what are the value of a y variable on process 1, 2, and 3? It would be 0, right? It wouldn't change because only the y value would be given only to the root process in MPI communication. And according to this uh, communication pattern, the only process that get the final result would be the root process, and that is process 0 here. In MPI, implementation, the root process could be other process too, but every process when you run the same MPI command, uh, every process here have to call MPI reduce, and every process has to specify the same root process. Otherwise, MPI will crash. So yeah, that's the reminder for using MPI. This is called collective communication. The reason it's being called collective because every process has to do the same thing. So every process has to call this particular function. Okay, let's take a look at another example. This is MPI reduce, and suppose that x, I represent x as a local integral, and y for the total integral here, and I want to suppose that x is 10. There are three processes. X is 10 and y is 30 for P0. X is 50 and y is 20 for P1, and x is 5 and y is 100 for P2. And suppose that the root process is process 0 for this MPI reduce uh, interface that being called on every process. And x is the first parameter. That means I want to use x as I want to collect the value of x from every process and add them together. So suppose that this is the global sum operation, and give the final output to the final result to y, and the root is process 0. What would be the x value and y value on process 0? The x value. So in MPI reduce, you would collect the value of x, right, from every process. So for process 0, you have x, of the x value is 10, P1 is 50, and P2 is 5. So when you sum them up, what do you get? You get 65, right? And so the 65 will be given to y on process 0, because I want to use process 0 as a root process for MPI reduce operation. So y for process 0 would be 65. What about x? X on process 0, what would the value of x be? X won't change, right? Because you don't assign anything to x. You just give x to MPI reduce x on every process. This is just an input. So MPI doesn't change anything on x. X would remain the same. So x on P0 would be 10, x on P1 would be 50, x on P2 would be 5. But what about y? What about the y value on P1 and P2? 65? Is this 65 or no, right? It's not. It won't change. It wouldn't change as well. So it would be 20 and 100. So now let's change the root. If I want the root to be instead of 0, if I want process P2 or a process of rank 2 to be the root, what would be the result of this MPI reduce operation? If the root process is process 2 or P2, then the final output would be given to the y variable on process P2. So y here would be 65. But y on the other process would remain the same, right? So when I change root from 0 to 2, then it would be the y result would appear here. Okay, that is MPI reduce. Now, this one is the MPI reduce for an array. Okay. So suppose I want to calculate a global sum for the array X on every process and get the final result on array Y on the root process. Suppose the root process is 0. So before calling MPI reduce, x0 and suppose x has two elements, x0 and x1, and x0 is 10, x1 is 2 on process P0, and x0 is 50, x1 is 3 on process P1, uh, and x0 is 5 and x1 is 4 on process P2. And after the MPI reduce operation, what would be the y value on y0 and y1 on process P0? See, the global sum operation for array would work like this. You will add x0 of process P0 to the x0 of process P1 and add the result of this to the x0 of process P2. So you put all, you accumulate all these x0 together and put around and give the final output to y0. And at the same time, you would uh, add x1 on P0 and x1 on P1 and x1 on P2 together and put the final result on to y1. So that's how you perform uh, a global sum using MPI reduce over an array of informations. So finally, the like in this example, for the if root process is zero, then the y would be y0 and y1 would be on process 0 would be y0 would be 10 plus 50 plus 5, so that would be 65, and y1 would be 2 plus 3 plus 4, and that would be 9. Okay, all right. Uh, so there are different between collective communication and point-to-point communication. Um, so in collective communication, every process have to call the same operation. It has to call the same MPI operation. And for example, MPI reduce, if you want to perform MPI reduce collective communication, every process has to call MPI reduce. If one of the process calls something like MPI receive, then your MPI program would crash. The next one is that the parameter being passed to the MPI collective communication must be compatible. By compatible, I mean that the variable and the data type uh, have to be on every process has to be the same type. And another thing is that uh, the root the root ID or the root or destination process, when you call MPI reduce, the root process or destination process, uh, the value given to that parameter has to be the same on every process. Um, if the value are different, then MPI would crash. Okay, and the output data would be given only to the output data P or the output data parameter of the destination process. That means the output will be given to the variable on the root process. Destination process and root process are, I mean, the same thing. And every parameter must be specify some value, even though that value could be null too, but you have to say to specify something to the parameter, every parameter in MPI communication. So in point-to-point communication, you match, in point-to-point communication of MPI, you match the sending operation and receiving operation using tag number. The tag number on send, MPI send and MPI receive has to be the same number. But in collective communication, there's no tag number used. But instead of using tag, it's used um, order of communication. So that means in MPI collective communication, every call to MPI reduce, for example, has to be the same in the same order. The MPI reduce being called on the same order are the one that talk to each other. As in this example, I have the code that call MPI reduce twice on every process, and suppose that the value of A is 1, C is 2 on every process, and then I call the first MPI reduce. Um, this one, the first one, this is the first MPI reduce. So the communication between them would be for this, and then the the second MPI reduce, the communication between them would be this set of communication. So suppose that in this communication, we have MPI reduce and use MPI sum, and the destination process is 0. So when you want to add them together, it would be like this. The every process would call MPI reduce, and then the according to the order of the matching communication, you would get the B value of 4 and the D value of 5. And let's see this one here. Let's take a look at this the step one uh, of MPI reduce communication. So the first parameter A is the input parameter, and in here for process one, process zero give a value of A as the input parameter, but the process one give the value of C as the input parameter. Process two give A as the input parameter. And suppose that the root process is 0 and the operation is global sum. So the value of B at the end of this operation would be what? What would be the value of B at the end of the first operation? So the result will appear here, right? The result will be assigned to this B variable on process 0. But what would that result be? You would get the input, the first one, you would get the value of A here, 1. For this process, you would get the value of not A, but C. Yeah. In this process, instead of getting the value of A, the programmer just, uh, trick us and give the value of C instead. And but for this one, you get the value of A. So the result would be something like this. Uh, After the first step, then you would get 1 plus 2. 2 would come from C here. And uh, B, result of B, the final result for this first operation would be 1 plus 2 plus 1. And 1 come from this A here. After the second operation, the input of the second operation would be C, A, and C. So C has a value of 1, A has a value of 1. Oh, sorry, say C has value of 2, A has value of 1, and C here has a value of 2. And the result, that is D, would have a value of 2 plus 1 plus 2 here. Okay, that is MPI reduce communication. What would happen if the root process change from 0 to 1? Then uh, what what would uh, what what would happen? I leave that for you uh, to think about it. All right, move on to the next one. Here, in this example, suppose I have x 10, y 30, and it's pretty much like the previous example. Here I get the value of x from process 0, value of y from process oh, okay. Yeah, I get the value of y here and get the result to y. Well, I would like to point out something here. actually I want to use this example to replace the value of y, but uh, but but actually this is wrong. This doesn't work because in MPI you MPI doesn't allow a parameter aliasing. This is called aliasing. This means you use the same parameter for different. You use the same variable for different parameter. MPI doesn't allow that. So yeah. So this one, yeah, actually I want to do use the same example as the previous one, but yeah, this turned out to be okay because this is a wrong use of MPI, and you cannot do this. So the parameter has to be the variable used for MPI parameter has to be different. Um, Now, what if you want the result to appear on every process instead of just on the root process? MPI has an interface called MPI reduce, and the parameter for MPI reduce is pretty much like MPI or reduce. The parameter is similar to MPI reduce, except that there is no root parameter or destination process parameter, because every process is a destination process, and you can implement MPI or reduce like this by using MPI reduce and then distribute the final value on process 0 to every process like this. But this calculation, I mean this communication method is inefficient. You can actually do something like this using butterfly communication pattern. This is basically just like doing a tree communication pattern on every process, and you somehow interleave it, do it at the same time, and you if you trace this, you would get the final result on every process. And this is most likely the MPI implementation that use that the implementation being implemented in MPI. Um, and here is efficient because you can see here that the number of communication step is log n for n number of process. So for MPI or reduce, in this example, you after you run this MPI or reduce command, what would be the value of y on every process? What would be the value of y on every process? Y come from the summation of x on every process, right? So x is 10 plus 50 plus 5, that would be 65. At the end of this operation, every y here would change to 65. The next communication, collective communication, is broadcast. So in MPI broadcast, you would send data like this, and you would call MPI broadcast, and the data will be distributed to every process, just like this. And for the communication pattern for MPI broadcast would be like this. You can use three communication pattern, and for n process, you would get log n step of communication. Um, this is also an example. Well, here I want to broadcast a value of x from a root process. Suppose that P0 is a root process. I want to broadcast the x value of this root process to every process. So after the first operation, the value of x would be broadcast to process or process 0 would be broadcast to process P1 and P2 and will be assigned to the Y variable and X variable on process P1 and P2 respectively, just like this. Um, and here I want to broadcast Y, but Y being given to X and Y. Uh, so when I do MPI communication, I have to specify the root process where the source process I want to distribute the data from to the root process. I have to specify the root process uh, in the MPI broadcast interface, and that root process has to be the same value on every when you call MPI bcast on every process. So this is the example. In the example of getting data from standard input, this is the trapezoidal rule example. Instead of using MPI send and receive, you can see here that I replace the MPI send and receive with MPI bcast. So that's pretty easy. Make it much easier to program. Um, the next one is the data distribution, and this is the example of vector operation. I want to I want to add vector x and vector y and get the result in vector z. So yeah, and you can write a rule for write it code for that. That's pretty easy. Uh, and So, the operation, the vector summation operation is pretty easy. This is sequential one. But what I want to point out here is the data distribution. Usually, when you suppose that I have three process, there are three kind to distribute three way to distribute data. The first one is the block distribution. Another one is cyclic distribution, and the last one is block cyclic distribution. Suppose that I have three process 0, 1, 2 here. For block distribution, suppose I have 12 element of data. You can see that for block distribution, I give the first four element to process 0, the next four element to process 1, and the last four element to process 2. But for cyclic distribution, the cyclic distribution will distribute data in a round robin fashion. So it would I would give 0 to process 0 and 1 to process 1, 2 to process 2, and then I round robin it to give element 3 to process 0, element 4 to process 1, and 5 to process 2, and so on. This is cyclic distribution. For block cyclic distribution, I give block distribution to every process, but the block size is limited. For example, the block size that I'm going to throw data to every process is the size of 2. So here I throw two value here, 0 and 1, to process 0, and then I give 2 and 3 to process 1, and 4 and 5 to process 2 in a cyclic fashion. And then I wrap it up, send 6 and 7 to process 0 and 1 and 2 and so on. This is block cyclic distribution. And MPI communication is very good for block communication distribution because in MPI, yeah, you yeah, that, we will talk about it in other example. Uh, for another MPI called MPI scatter. MPI scatter, this is another uh, collective communication that we can use to distribute data from one process to another process. So in MPI scatter, there are so many parameters here that I'm going to skip. And yeah, so this is what happened. The first parameter is the input parameter. I want to send data from this parameter to every process. and every process have to supply this receive buffer parameter to receive the data from the sender, and I have to specify the amount of data that I want to send to each process here in send count and receive count, and the root process or the sender process, I have to specify it here as the source process here. So this is what happens. Suppose that 0 is a sender process, and I want to distribute it, the element of this array to every process by calling MPI scatter. So when every process call MPI scatter, the process 0 will assign, will take this process, will take this the send buffer or the send array, and then MPI would assign x0, the first element, to process 0. The next element x1 it would send to process P1, and 2 to process 2, and 3 to process 3, and so on. The distribution will be done based on the rank, based on rank number of every process. So process 0 will always get this data, the data at the element 0. On the other hand, in this case, I want to send one data to each process. But if I have an array of 8 and I want to send 2 data to each process, then it would be distributed like this. X0 and X1 would be distributed to process 0, and X2 and X3 would be given to process P1, and X4 and X5 would be sent to process P2, and so on. So it would be like this. Um, so that is MPI scatter. And here, this is an example of using MPI scatter. So I'm going to show you this one example, the first one and the second one. The first one, I will send the data from B array, and I will send 2 data from the B array and get the result in the A array. And the A array of every process would receive two elements from process 0. See, this is the root process here. Root process is 0, and the communication pattern of this command is here on the left. Suppose I have 8 elements, so the 0 and 1 element, I want to send 2 elements to every process. It would be distributed like this. Process 0, even though it is a sender, the element of A would be sent to the B on the sender process. So B would receive 1, 0, 1, and 2, and 3, and 4, 5, and 6, 7 to every process. But let's take a look at this one. This one is a scatter and send only one element to every process. So in this one, I would send only 0, 1, and 2, and 3 to every process. So the number of elements being sent, that is important. Okay. But here, I from the previous example, the root process is 0. What if the root process is 0, 1, 2? What if the root process is 2 instead of 0? What would happen here? What would be distributed to every process? The answer is the same as before. Process 0 would get 0, 1, 2 would get 2, 3, 4 would get 4, 5, and 3 would get 4, 5, and 4 would get 2 would get 4, 5, and 3 would get 6, 7. This, it would be the same as before, no matter what the root process is, because the distribution is being done based on the rank number of the process, right? So that is a scatter. That's how you distribute data in an array to every other process. Now for gather, gather is another collective communication, and for gather, uh, gather is the collective communication that do something different, the opposite of scatter. In gather, every process will send a piece of information in the array send buffer, and it will send this amount of data array, this amount of array element, and the output, the final output will appear on the receiver buffer, and it will appear on the receiver buffer of the destination process. So for example, this suppose that the S destination process in this case is zero, process zero. And I have one element from every process that I want to send to to a final array on process zero. And you can see here that every process send its data, one element of data to process zero, and the process zero will put this element in a final array, and the location of the element on the array is assigned of the final or the result array is assigned based on the rank number of the sender process. The same thing here. If I want to send two elements from every process to the to process zero, then process zero would put the first two elements that will be the first two elements from sent from itself at the beginning because it has a rank number of zero, and um, and next one it will put the data being sent from process P1, that will be X2 and X3, and followed by the data sent from process P2 and P3, and then you get the final output. That's how MPI gather operate. So yeah, let me give the example again. This is the example of MPI getter that will send two data from array and array A to process to the variable B, and that variable B would be the variable B on process zero. I'm sorry, this is wrong. One here has to change to zero. Okay. Yeah, I use this. That's the wrong interface. I better refer to this interface here. This the root process or the destination process is process zero. And another example would be this one. This one, instead of sending two data to the destination process that is process zero, I send only one element. And let's see how the communication pattern turn out. The for MPI gather, the process zero would send the first would send these two elements that is in A, that means the 0 and 1 to itself. So it would put 0 and 1 as the first two elements in array B. And then the MPI gather would put 2 and 3 next to 0 and 1 because 2 and 3 are sent from process 1, and then it will send it will put the information from process 2 next and process 3 next. So finally you will get this result, the final result. But on the another example where you only send one data instead of two, so you can see here that process 0, 1, and 2, 0 would just put 0 element from A, and 2 from 2 element from process P1, 4 from process P2, and 6 from process P3 into this array, this final array. So this is different. Okay. And if I change from this is MPI gather. So in the previous example, the root process or process 0 is the destination process. But if I change the destination process to process P3 or P1, the output would be the same, right? The output would be the same as the previous example. Okay. So that is MPI gather. And you can use MPI gather in here. This is an example of how you use MPI gather. So basically, uh, when you assign array, well, when you get the data, say for local local B and you want to collect local B from everybody to process 0, you would run code like this for MPI gather. So this is the destination is 0, all right? All gather. MPI gather produce result at the destination process. But what if you want the result to appear on every process in MPI? You would use all gather. And in all gather, the parameters are similar to that of gather except the root process. There is no root process or destination process here because the output would be present or would appear on every process. So this is the example as before, and like when you run MPI all gather on every process, you would get the same result on every process in the array B of every process. So can you write a C code to implement MPI all gather using gather? Yeah, you can think about it, like how to write that C code. Okay, I'm gonna move on to another example, matrix vector multiplication. So I think we are familiar with matrix vector multiplication, and and it's something like this. I'm not gonna repeat that again, but the sequential code is pretty easy. You like take a row and dot product with the columns with the x, and then you get the y. And in C, well, this is how this sometimes programmer do something like this to especially for parallel processing when you want to uh, uh, represent the two-dimension array, sometimes you would use one-dimension array. And by using one-dimension array, you kind of writing your own code to simulate the two-dimension. But this would be easy because when you have a piece of data in one-dimension array, you can do the block distribution very easy. So that's what happened in the parallel code. This is a sequential code. In the parallel code, how would we distribute the data? Suppose I have 4 processes, and then I want to do the parallel matrix vector multiplication. So the easy way to distribute data on every process would be using block distribution on every piece of data. For example, the vector A, I would give this first chunk of data to the process 0, and the next one in the block distribution pattern to process P1, P2, and P3. And I do the same kind of block distribution over the X vector and the Y vector. So it's like this. So every process has separate piece of information. See, because MPI run on process, and every process have separate memory space. So process P0, we have this piece of A and X, and this piece of X. That's partial information about X. So how do you perform? I mean, like a process P0 is responsible for produce Y0 and Y1. Process P1 is responsible for produce Y2 and Y3 and so on. So how does P0? How can P0 calculate Y0 and Y1. In order to do that, P0 has to do something here, right? P0 have to get the information of every have to get the x vector, x value from every process and make it the x vector. So in doing that, you have to, before every process perform a matrix multiplication, a dot product, every process has to do what kind of communication? It has to do this, right? For matrix vector multiplication, the parallel version, every process has to do MPI all gather first. It has to be all gather because you want the result to appear on every process. The result, the final x vector have to appear on every process, and then you can do the local computation of every process and get the y value. So that's the how to use gather or gather. Now let's move on to MPI data type. And MPI data type is basically, this is the derived type. And I'm gonna go over this quickly. But how do you? I mean, if I want to define my own type, if I want to send array from one process to another process, that easy. But if I want to define my own type, how would MPI do? It what M, what MPI do is this. It just first of all, it have to uh, it has to collect some information about the data. For example, if you want to send the value of A, B, and N in one shot, I mean in one one MPI communication. So you have to define the new type, and in this type, it will consist of A, B, and N, but you have to keep MPI the address of this variable. And it has to be, for example, if the address is 24, 40, and 48, so what you have to keep to MPI are these information uh, is the couple is the couple of information about a pair of information about every data element. For example, since A has a type of double, and you want to send A first at the first position, then the relative offset of the A is 0. Next, B, you want to send B, and the memory address of B is 40, which you have to keep MPI the type of B, and then the relative offset value of the position of B to the position of A, which is 40 minus 24, that is 16. And N, also the same thing, N is the integer. So you give a type integer here, and the relative location of N to A is 24. 48 minus 24. Okay, so this is the function how to you create that kind of information and a new type. After you get that information, you can use that information to create new type for MPI. And here there are the detail here that I will. This is the when this is the interface, MPI interface, that allow you to create that type. So you just supply what I just showed you earlier information into this interface, then it will give you a new type, and you can use that new type to send in MPI information. The receiver process, the sender process and the receiver process supposed to do the same thing, so that the MPI on the sender and the receiver know where the data are A, B, and N are. So and this is how you get the address information of every process. Of every element. And after you create the type, you have to commit the type and then use it. And after you finish using that type, you can free data structure, the MPI data structure that uh, uh, used for that type. And this is an easy example on how to create that A, B, and N data type. So here you get information like this. You give the type, you give the address, the displacement. I mean, the element of every variable that you want to send. You want to send A, B, and N. Those are one element. And what are the type of these A, B, and N? They are double, and integer. And to calculate the displacement or the offset, you basically use MPI get address to get address of every variable, and then you just subtract them, get the displacement, and then put everything in MPI create struct, and you get the new type. The new type is input MPIT, this one right here. You commit the type, and after that, you can use this type. So in the trapezoidal example, instead of sending A, B, use MPI bcast to send A, B, and N separately, I just use MPI bcast to send this one, just one data element. So next for performance evaluation, to do the performance evaluation, you have to use something called MPI barrier. And using barrier is the same thing as when we study p-thread. P-thread, you use barrier, and then you measure the time, and you divide the time, you get the elapsed time. And the same thing here, MPI have MPI W time to get the wall clock time for the MPI for the process. Usually, you would measure the performance on process 0, and you print the output on process 0. And well, for sequential process, you can use get time of day, and that is the system called get time of day, and then you divide, you minus them, you minus finish and start, you get the elapsed time. For MPI, but for MPI, you have to use something like this. Before you measure the start and stop time, you have to use MPI barrier. In using MPI barrier, suppose you want to measure the performance of the execution of this code. So before you start use MPI wall clock time to get the start time, you have to use MPI barrier. MPI barrier is a collective communication, so you have to use it on every process. And when the code, so the result of well, the behavior MPI barrier is like every MPI process will, when it arrives at MPI barrier, we wait for every process in the cluster to arrive at the barrier, and then it will start at the same time. When it starts, you can first measure the start time, and then when your code finish, you can measure the finish time. In this way, you will know which process has the you get the elapsed time of every process on every process. Then you can use MPI reduce to find the maximum elapsed time or minimum elapsed time or whatever, and then use and then report it. Usually you would use MPI rank 0 to report it. For performance, I would say this: when you do parallel processing, um, it's, um, parallel processing is good when you have a lot of data or when you have a lot of work. Like when you want to build a house or something, and yeah, you can, like, suppose you have only one or two house, but then you hire like 10 1,000 people, 1,000 workers to come together and build two house or one house. you know uh, it's not gonna be faster than just a few subcontractor do it, because most of the people won't have anything to do. So you would waste a lot of money to hire a lot of people. So you would hire like 10,000 people to build the whole housing project, to build หมู่บ้านจัดสรร or something like that, so that is like that's how you use parallel processing. And the result, the same thing appear here when the data size, this is matrix vector multiplication. When the data size is small, you would get the result like you will get the when the data size is 124, then you use one process, you get 4.1, and when you use 16 process, you get 1.7. So you use 16 process just to reduce 3 seconds. That is, waste of a lot of processor here. But on the other hand, if you look at this, this is the when the order of the matrix is 16,000. The problem size is huge. When the problem size is huge, you can see that using one process is like 1,000, 1,100. Second, millisecond, whatever. And then when you use 16 process, it reduces significantly. So this is the power of parallel process. But when you use parallel process, that you have to be careful, that you have to get the right amount of data of problem size. And the comparison between sequential process and parallel process, they are that's what called speed up. Okay, speed up. And the speed up for each process is called efficiency. So, and yeah, and when you calculate the speed up using those number, and you can see that the speed up, like speed up is basically how many times faster can parallel processing do for you. So this one you use 16 processor, and see on the big problem side you get 15 times speed up. That means 60 times better. So that is good, right? You use 16 processor and you get 16 times or 15 times better than the sequential processing. But if the problem size is small, you use 16 processor and you get only 2 times better than the sequential processor. That is not good. Okay, that is speed up. And the difference here, that is what we call scalability. Scalability is something like that. Scalability, there is strong scalability and weak scalability. It's just like what I just told you. It just they just rephrase it in the book like this. Strong scalability, strong scalability. What I told you earlier, what weak scalability. If your program has a weak scalability, it's okay, it's good. If your program can do the weak scalability, that means when you increase problem size and your performance can you can get like 16 times performance, just like in the previous example. That is good. That is good, but they call it weak scalability. People always want something more. Strong scalability means even one processor, even small problem size, you would get this high scalability. You would get scalability like 16 times scalability, no matter what the problem size is. So that is strong scalability. But weak scalability, that's the one, that the okay one that I just show you. So I think I don't have time to cover this sorting algorithm. Uh, and I think I'm going to skip this one, but you can read it in the book. It's a good example for sorting algorithm. And if you want to do some sorting in parallel, and whatever problem that you encounter in your project, and you want to use, and first of all, if your problem is the problem size is big enough, if your problem size big enough, you want to solve a lot of number, then you better look at the book and follow this sorting example. They have some good one here, and yeah, that's yeah. I'm gonna skip this one. The last one I want to just say it a little, that MPI, when you use MPI send here, you have to be careful when using MPI send. Usually MPI send is okay, but that you could have some the problem is that MPI send data to buffer, And sometimes when it send data to buffer, it have to it will behave differently. If the data is it has a lot of data, if it has a lot of data to send, it would block. But if the data can be copied to the buffer, then the MPI send would just won't block. And when the MPI send block, uh, you can have the situation called deadlock. And if you want to use MPI further, I would suggest you to read this in the book. It's called Unsafe Feature of MPI. There is a way that you can really do MPI implementation safely. So, I'm not going to detail because, but we basically cover, the very good information about MPI already. If you want to do it in your serious project, then I suggest read the unsafe feature of MPI, and that and this would help you a lot. Okay, and MPI send receive and so on. So that is that is what I want to cover here today. So we basically do see MPI communication and MPI collective communications and the performance. So I think that would be it for today. I think we just make it at 4. And thank you. And I'm going to send this slide to, I think one of you have the slide already, and I'm going to send this slide to Ajahn Somchat. And also, if I have any other information, if the video work, and then I put it on and give it to Ajahn Somchat. All right. Well, so today I think we will stop.